Okay, hello everyone. Welcome to another episode of Q&A about history of science and technology. Happy to try and answer questions, specific and general, about either recent history that I've been involved in or history from the past that I might have studied. Let's see. There's a question from Aaron here. I'm afraid I don't know the answer to. Did any ancient unit systems, number systems, use base 10, or did they all use more easily divisible bases like 12, 20, 60, and so on? So the thing you have to understand about the representation of numbers is that, the idea of positional notation that we have today, that's the Hindu-Arabic number system, is something that, well, it came to the West around 1200, particularly through the work of Fibonacci, his book Liber Abaci, the book of the abacus, which kind of promoted Hindu-Arabic positional notation type numbers as the kind of the magic bullet for merchants and so on, trying to work out how to do their computations. But there were very different kinds of number systems. Like, for example, the Roman number system is one where, well, there sort of is a base. I mean, it's kind of base 10, but it has, some base 5 pieces, there are X's and V's, and there are C's and M's and D's and so on in the number system. So it's kind of a complicated mixed radix system. Now, for example, the Greek number system, interesting story there, that was, let's see. I mean, there's the names of the numbers. Yeah, I mean even in ancient Greek, certainly the number system had the name of numbers. Such and such chi deca. It's like tetra chi deca. I think will be 14. Is 4 and 10. So that's already a kind of a base 10-like system. But there were a lot of funkinesses in the actual notation. So, for example, in ancient Greek, the ancient Greek number system, they used the letters of their alphabet as the sequential numbers. So alpha was 1, beta was 2, gamma was 3, et cetera, et cetera, et cetera. It's an interesting, for somebody like me who's been interested in things like language design for a long time, the ancient Greek number system is a good example of a mistake in some respects, because what they did was they had the letters of the alphabet in the order of their alphabet represent numbers, but some of those letters went out of circulation as letters to be used in text. So sampi, digamma, these are things that existed in the sort of ancient Greek numbers, ancient Greek alphabet, and those got burnt into their number system. I think sampi is 60, if I remember correctly. But sampi is not a word that is not a letter name you usually hear. It's alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, et cetera, et cetera, et cetera. The usual Greek letters. You don't hear sampi or digamma or copper. Those are the three that I think went out of circulation. Digamma is like a W sound. Copper is like a Q-like thing. So when people were labeling, I'm not sure if by the time of Euclid, I think it had already gone out of circulation. And so when Euclid had to label geometric diagrams, and it's an interesting thing that Euclid did have geometric diagrams that got labeled, and he would use alpha, beta, and so on to represent magnitudes of angles and things like that. And if you've got 3 angles to indicate, you might use alpha, beta, gamma. You might use or if you wanted to use P, Q, R, the corresponding letters, Greek letters will be pi, copper, rho, so to speak. Let's see, digamma. What is the sound for digamma? I think, yeah, digamma is a W-like thing. Sampi is this, is I'm not sure what sound that makes. But in any case, in the Greek number system, what they did was they didn't really have positional notation. Like when they had the number 60, they had a letter that represented 60, and they appended to that letter, it might be, Sampi beta, might be 62 if I remember correctly. but it's not like you were using the positional number, whatever it is, alpha, beta, gamma, delta, epsilon, zeta. So it would have been zeta, beta if it had been a positional notation, but actually the thing that represented the 60 was a different letter from the thing that was representing a 6, but moved into the other position. So I think the answer is yes, there were ancient number systems that were base 10. The Babylonian system, from which we get our hours, minutes, seconds, and so on, was a base 60 system, and that was that particular way of doing things, but that wasn't the universal thing. And I guess people have had 10 fingers for a long time, and that's been a convenient way to do counting for a long time. In fact, I'm not even. I think it might be the case that the tally marks, which is some of the earliest number representations that we have, where you're just marking on a bone or something, you're just marking, tally marks to indicate things. I think this notation of putting a slash through 5 of them, I think that's pretty ancient. And so that would be another example there. Let's see. Oh, there's a question here from Mikhail. What is the history of design patterns in software engineering? How did people come to them? Well, let's talk a little bit about the history of programming languages and the general way that one sort of specifies software. So I guess it began in the mid to late 1950s with kind of the arrival of somewhat standardized computers. I mean, the very first computers like the ENIAC and so on from the mid-1940s had been, mid to late 1940s, had been kind of one-of-a-kind machines. And there was sort of increasing standardization with, what were the companies? Burroughs, Univac, and IBM was a big player. I would say in the mid to late 50s, there were things like the early sort of standardized IBM, maybe the 709, if I remember correctly, predecessor of the IBM 360, which was sort of the big sort of workhorse mainframe computer that arrived in the early 1960s. But as these computers that were somewhat more standardized kind of came into existence, so there was a desire to have somewhat more standardized kind of programming mechanisms. And it wasn't the case that, oh, you are using the such and such, the ILIAC 1 computer or something, so this is how you program it. And if you're using some other computer, this is how you program it. There's a sort of standardized way of doing it. And so I think the early, there were a variety of early languages. I think there was a thing called autocode, which I know little about. The first one that I know anything significant about is Fortran. Fortran was I think pretty IBM connected, if I remember correctly. Fortran, the name meant formula translation. And so the idea was that you would be able to write a mathematical type formula that with things like X plus Y times Z or something, with the plus signs and the stars and so on to indicate those operations, and that formula would get translated into the machine code of the computer. And I think Grace Hopper was the person who if I'm remembering correctly, was the leader of that effort to make Fortran, if I remember correctly. The early, the big emphasis was, can you take something which is sort of a naturally written mathy formula and translate it into the machine code of the computer? And there were things about the machine that were, like, for example, what would it print out? Oh, it would print these, you could print out a string of data. And so there was a Fortran format statements, which where you would say, oh, I want to just print this number out. And for example, one of the things that was kind of an awkward thing was printing a string, like the result is. And then just the number, you could print the number out. That was a well-defined way to do that. One of the issues was that there was a desire to sort of specify how wide the thing you printed out was going to be. And so the number will be 6 digits or whatever it was, and there will be a way of specifying the format for the number. Then the way of specifying the string was these so-called Hollerith codes. So you would say things like 13H, and then you would give the string you were going to specify. I guess people hadn't figured out delimiters for strings. The idea of quotes around strings to indicate where does the string start, where does the string end, that wasn't a thing at that point. So in early Fortran, even Fortrans that I used in the 1970s, mid-1970s, it was still the case. You would say 13H or something, which means there are 13 characters that are coming in this string. Those are what you're going to include in the output. H, the Hollerith name, was in kind of recognition of Herman Hollerith, who had been one of the early people in the origination of IBM in the early 1900s, when it was the kind of a Hollerith tabulating machine had been the thing used for the Census Bureau in the US, where they were using kind of cards as a way to tabulate kind of census results. You would get a card, and you would have punch holes in it, and you would be able to sort of run some kind of rod through the place where there were those holes punched, and that was the way of representing, how many people were. And you would sort of pick up the cards, and the ones that sort of came out with the rod that you put through were the ones that included that particular hole that was punched, and so on. I mean, this whole technology of cards was quite old. I mean, this had been invented by Jacquard for the Jacquard loom around 1800 as a way of specifying kind of weaving patterns for looms. And that was then used for tabulation early 1900-ish by what became IBM. And then that was the thing that became what was used as the principal way of programming large computers, was card decks, big stacks of these cards that were my gosh, I'm forgetting. You used to use these on card punches, and the way it would work is you would be typing, and you would be, and then you would, and that would be sort of punching holes in successive columns on the card. And for example, if your line of code in your Fortran program, for example, ran too long, you would go on to another card, and you would punch out something in the continuation column, which is I think column 6, but I can't remember for sure, of an 80-column card. That would be the indication that this was a continuation card from what would be from the previous card. And of course, the thing that was always the horror was you would have these card decks. It might be a big, thick stack of cards, and the real horror would be if you drop the card deck and you've randomized the collection of cards. And then I think one of the sort of technologies that came in was somehow numbering those cards when they got generated, so that you could so that a machine could automatically resort them into order. Fortunately, I don't recall ever dropping a card deck, but you would tend to put them. The typical way of using a mainframe computer, certainly the first ones I used, was there would be these operators who would be the people actually enabled to be, the high priests, enabled to actually be with the computer, and you would put, in these wooden pigeonholes, you would put your card deck in there, and I think you usually put a rubber band or something around it, and then you put it in there. Some mysterious, it feels very Delphic, it's like the Delphic Oracle or something. You're putting things through slots, and then the machine is running your code, and then somebody would sort of take the card deck, and then half an hour later or something, you'd come back, and there would be a folded line printer output in your pigeonhole along with your cards again. So somebody would have run the program and then given you the results back. I have to say, this was probably 1977, was the first time I was actually sort of in the room with the mainframe computer. I worked at Argonne National Lab near Chicago for a summer in 1977, and that was a place where they trusted the physicists or whatever, or the sort of young proto-physicists like me, to actually be in the room with these expensive mainframe computers, where you could actually interact with it directly, so to speak, rather than handing it to the high priests or whatever. And I suppose also, gosh, it's a long time since I thought about this, but I worked the year before that, in 1976, I worked at the Rutherford Lab in England, which is part of the, it was part of the nuclear physics and particle physics research apparatus in the UK. And the Rutherford Lab, they were developing a time-sharing system. For some reason, I think it was called TAS, time-sharing system, and that had displays where you could interactively do things. At least you could interactively submit jobs for the computer and so on. That was still the time when computer terminals, they were obviously cathode ray tubes, but they were called VDUs, visual display units, as the thing that was, I guess terminal may have been an American word, which gradually got sort of exported around the world. I mean, a number of these computer terms were different in, for example, the UK and the US. Like, for example, the term for memory in the US is storage or store. In the UK, or at least it was. I'm sure it's now memory. And for example, I remember the concept of booting a computer was definitely not a British computing terminology thing. One would talk about running the initial instructions as opposed to booting a computer. But in any case, I digress talking about the history of programming languages. So I think it was 1958 was the origination of Fortran. Around the same time was COBOL, and COBOL was intended as a business language, and it was sort of intended to be, if Fortran was take math notation and put it on the computer, COBOL was take English language and put it on the computer and make things be like pseudo-English statements. So both of those in Fortran, the style of writing code was, some aspects of it are painfully similar to today's modern traditional programming languages. I mean, Fortran was very much into, Fortran did not have recursion. You couldn't have one function that called another function repeatedly. Fortran was, it had its means of control flow was a lot of go-tos. If blah, 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 go to instruction such and such, or go to label such and such. In terms of modularization of code, Fortran did have early Fortrans, Fortran 66, for example, from 1966, that was a Fortran that I used, for example, had the notion of subroutines that you would call. The term function was a little bit more recent, but subroutines that would be the things that would be a block of code and so on. And there would be local variables in those subroutines, and there would be global variables. And one of the horrors of large Fortran programs were these things called common blocks, where you would basically define global storage for your program, and you would name these pieces of the common block, and you would basically be able to access these sort of global variables across different parts of your program, and things got often very spaghettified in doing that. But I would say that the the attempt to make sort of a principled early languages, Fortran was very much a practical sort of engineering-oriented language, COBOL, business systems language. There was an effort, I think started in 1957, 58 or so, to make this language called ALGOL, which would be a more principled, kind of more theoretically based language. And there was sort of a big committee of people that got involved in doing that. It was the place where these sort of formal specifications, Bacchus-Naur forms, formal kind of parser specifications were kind of a big thing. ALGOL got very overblown in its specification and was never implemented in full. It was sort of a stimulus for future programming languages, but it never was fully implemented, at least to my knowledge. There were versions of it, there were sort of spin-offs. Like I remember I didn't like it very much, but I briefly was exposed to a language called Simpol, which was a simple version of ALGOL that I was exposed to around 1972 or so. But to be clear, even in the 1970s, early 1970s, serious programmers wrote in assembly language. Serious programmers writing systems level code did not imagine that they would write in a, quotes, high level language, even at the level of something like Fortran. But, the next kind of really big thing that came on the scene, well, a language called Pascal, developed by a person called Niklaus Wirth in Switzerland. Pascal was kind of I would say a cleaner and more principled language. There were also a series of other languages. There was a language called BCPL. I don't remember what BC stood for. It, I think, originated in London University. And that there was sort of a version of that called sort of a spin-off from that called B, and then famously the next spin-off from that was called C, and that became the C programming language. And I think that the thing to understand is some of the programs, when people were writing big application programs, they were usually writing it in things like IBM 360 assembly language. Every separate computer had a different assembly language, and that would be kind of a lock-in for, for application programs. Oh, they were for IBM mainframes, and that was all they were for, because that was the only thing that instruction set worked with. And I think, just as has happened with microprocessors, there was an effort to clone the instruction set. And as I recall, there was a big sort of antitrust showdown about cloning instruction sets for mainframe computers. And obviously the issue there is whether the application software is locked to a particular mainframe computer. And this was sort of a thing that played out in the 1960s, early 1970s. But in any case, the thing that then happened in terms of programming languages, serious stuff was written in assembly language. Then there was starting to be things that were written in other languages. I think the original Mac operating system was written in Pascal. And famously, the C programming language was developed at Bell Labs to write the Unix operating system. So there had been an operating system called Multics, which was an earlier quite big operating system. I should have explained that one of the things that happened in the computer industry was, IBM was sort of the big player with its big machines. Then Digital Equipment Corporation came along. This is now the 1960s, and came along with its PDP series of computers, starting with PDP-1. And these were kind of smaller computers that were still serious computers. And for example, by the time it was the PDP-10, PDP-10 was a pretty serious computer. It was a computer I used quite extensively. It was a computer actually available over the ARPANET. By the mid-1970s, that was sort of a serious contender for a sort of research-oriented computer. And that was, the PDP-10 ran the Multics operating system, as I recall. Which I assume was written in assembly language. Unix was a kind of stripped down Multics. That was its original concept, and for its creation, a new language was created, the C programming language, and that was basically Dennis Ritchie and Ken Thompson, who were the originators of these languages that somebody's asking, did I meet these people? Yes, I certainly met Dennis Ritchie, Brian Kernighan, who came on the scene a bit later. Ken Thompson was the originator, I think, of the sort of operating system and C story. I never met Niklaus Wirth, unfortunately. Alan Kay I have met, yes. And Paul Allen, I don't believe I ever met. Niklaus, yeah. So Dennis Ritchie actually was sort of interesting background. He had written his PhD thesis about sort of theoretical computation, and particularly these things called register machines, which are sort of simple idealizations of computation. And in developing the C programming language, one of the things that was sort of nice about C was this very minimal approach to everything, very minimalist kind of way of presenting things. And I think maybe that was a little bit of a spin-off of Dennis Ritchie's earlier work on things like register machines. But that was one. The original machine, I believe the PDP-11 which was a small computer, was the original thing on which the C programming language was originated. Although the purpose of C was to develop the Unix operating system. The Unix operating system's original purpose was to run telephone switches for the Bell system for AT&T. And I was briefly a consultant in the Bell Labs, and sort of interacted a bunch with the Unix group. That was in 1983-ish timeframe. I had so that's and at the time there were a whole series of computers that had been constructed by the Bell system to run phone exchanges, and they were running, I think, a version of Unix called Unix RT, a real-time version of Unix, where, to my early amusement, so to speak, there were these system calls that were things like, initiate a trunk phone call and so on. Those were sort of part of the operating system. But the thing that happened with Unix, among other things, was that Bell Labs didn't really, they had developed it for the purpose of running phone switches, and any other use of it was like, well, whatever, we can just give it away. And that was an important sort of stimulus, was Bell Labs, AT&T, was just sort of letting the Unix operating system be used elsewhere. And a bunch of companies started using Unix on their computers. And that was sort of a big theme of some of the, for example, early workstation computers, as now in 1980s, was running Unix. They didn't all run Unix. Some of them ran other kinds of things, and there were even attempts to make a non-Bell Labs entangled Unix, a thing called Coherent, which was an attempt to make from scratch a version that didn't have the licensing issues that the Bell Labs Unix had. But in any case, that we're sort of skipping ahead in terms of programming languages, because C was sort of a clean programming language. I think Pascal, like C, had sort of nice encapsulated functions. It had recursion. It had all those kinds of things. It still had, all those languages had, go-tos and labels and things like this. They all had basically the same set of operations. I mean, conditionals, function calls, transfer control by go-tos, things like that. They all were the same kind of stuff. And they started to have, C, I guess, I think maybe Pascal has this as well, has the kind of struct data structure type, build a more complicated thing that you can encapsulate in a single variable. C had a particularly clean way of dealing with pointers, has a particularly clean way of dealing with pointers, pointers to memory references and things like that. But so that was kind of the, let's see, the early history of those things. Now, there were some other entrants, like, for example, BASIC was a thing that appeared on the scene that had been developed at Dartmouth by John Kemeny, who was, again, very much a sort of theoretical, mathematical logic kind of person, who I think rose to be the president of Dartmouth College, and who was big on sort of trying to, this is 1960s, on sort of introducing this idea of computing into into things at large. And I see BASIC as being sort of the first of probably 5 waves of let's teach the world coding. It's probably one of the better ones, actually. And they've all been, they've gone in sequence. I mean, I'm afraid I would say that, one of the challenges is when you don't have, with Wolfram language and our computational language, as soon as you're writing code, you can write it about things, because the language actually knows about the world. It knows about, cities and planets, and it knows about all these different algorithms and graphics and audio and all that kind of thing. So it's very easy to start actually doing computation about things. But when you're dealing with a raw programming language whose real objective is just tell that computer how to, move its bits around, it tends to get rather dry rather quickly. And there's sort of, and that's been a kind of a curse of people trying to sort of teach coding to the world is, well, what are you going to code about? I mean, it kind of reminds one back in ancient Babylon, there were these scribal schools where scribes were learning to write. And, yes, you learn to write, but then a large part of sort of the scribal school was learning about different topics that you could then be writing about, so to speak. But I think, in some of these efforts to let's teach coding with low-level languages, it's kind of, what they might have called themselves high-level languages, but I call them low-level languages. They're not full computational languages. They're just programming languages. It's, you kind of run out of things to program about rather quickly, which is something that, with our kind of computational language story, the great thing is that you actually get to write code. You get to sort of present things computationally about all these different things in the world. And that gives you a lot of sort of mileage, gives you a lot of potential to actually teach in an interesting way about these things. But anyway, BASIC was an early entrant in sort of the story of programming languages. It was clean, it was simple, it was quite unstructured, but it was it was a good thing. And BASIC got a big boost when Bill Gates kind of started making versions of it for early personal computers and so on. Just as Pascal had gotten quite a boost when it was, it was particularly the company called Borland and Philippe Kahn and so on had developed a, I'm forgetting this history. There was a thing called UCSD Pascal that somehow showed up, and there was a thing called P-code, which was a kind of a runtime for Pascal that somehow started showing up on early personal computers. It didn't quite make it, partly because sort of there was this kind of Borland versus Microsoft showdown, where Microsoft was kind of on the high end of pricing of software. Borland was on kind of the everything costs $100 or less, and Microsoft won out in that. And so I think the Borland, Pascal, and they were also into a language called Delphi, that kind of that lost out in that story. But I think the question was about sort of design patterns in programming languages. So by the time one's got to C, one has recursion, one has structs, one has pointers. The next sort of big thing, I suppose, was the story of object-oriented programming. And there were some other entrants in the programming language world. There had been Lisp, which was done by John McCarthy, late 1950s, originally as a more theoretical kind of thing. And Lisp kind of really had a hard time becoming practical. And, back in the early 1980s, there were a couple of companies that were trying to make Lisp machines, because on sort of a general purpose computer, you couldn't really have sort of the full Lisp story with all of its kind of sort of profligate use of memory and things like this. Wasn't something that was sort of readily usable for the things people imagined they would use it for. You just couldn't get the efficiency. And remember, people were still a lot programming in assembly language at that time. I think if history had played differently, Lisp might have been a bigger force in the development of programming languages. Really wasn't much of a force. Another thing that originated was Smalltalk. I never used Smalltalk. I didn't know about it in great detail. That was, I think, Adele Goldberg was the person involved in that at Xerox PARC. And it had been something that was built to kind of support the bitmap display terminals and the early user interfaces that were developed at Xerox PARC in the early 1970s, I guess, early to mid 1970s. Smalltalk, I gather, was sort of an early model of object-oriented programming. It was sort of forced into that picture because when you're putting up windows on the screen, they're kind of like objects that you have to sort of poke at, peek things from. You have to poke and peek with the names in BASIC for accessing individual memory locations, kind of going underneath the hood of kind of what the sort of the high level description of you've got variables and so on. They was like memory location such and such, what's there, and things like this. The thing that once you were building a Windows system, you kind of had to be dealing with these somewhat ironically, one might say opaque objects, even though they were windows that, of course, were not windows you look through. They're windows that you are putting text into and so on. And I think that was what drove that kind of object-oriented programming concept. By the way, there have been other languages which had some significance, like Forth was a language originally developed for controlling radio telescopes. It was a very minimal stack-based language. That sort of had its lineage, ended up with kind of the stack-based approaches of things like the PostScript page description language, things like this. It was the kind of embedded language that I suppose these days has been taken over by languages like Lua and so on as sort of the simple embedded language type thing. But in any case, from sort of the kind of the object-oriented programming thing, that led to when was this? This was the late 1980s. I'm skipping a few things. So a big sort of fad was this notion of structured programming. Not quite sure what that really meant, but I think it was, don't just have random go-to statements all over your code. Having the program sort of be running this piece and then randomly start running another piece. It was more like keep the thing more modular and know you've got a subroutine here that's well encapsulated, and then another thing can be run over here. One of the things that was part of that story was the Ada programming language, developed by and for the US Defense Department in the early 1980s. And the concept of Ada was, oh, the Defense Department is getting all this code written in all these different languages. It's very hard to verify. We're going to have this one standardized language that all kind of contracted defense contractor code is going to get written in. But I think it was a very committee developed language, and it ended up being very big, just like Algol and so on. And I don't think it was ever fully implemented. I'm not sure. And there was sort of a lot of kind of weirdness where it was like, well, we're really going to write it in Fortran, let's say, or C or something, but we're going to translate it into Ada in some nominal automatic translation thing so we can deliver it for the contract, even though nobody could ever read the code. But then this must have been the mid-1980s, this idea, everything became about object-oriented programming. That was the story of everything. A decent approach for things to do with things like user interfaces, not a good approach, in my view, for general computational language. The thing that, and there were a couple of different sort of competitors there. There was Objective-C, which has sort of got adopted by Steve Jobs at Next. That was, oh my gosh, what was the company called? Sandy something or other. Oh my gosh, what was it? It was in, forgotten. Anyway, that was the company that made Objective-C. And then there was C++ made by Bjorn Stoustrup, who I knew slightly when I was at Bell Labs. And C++ was I think, from very early on, viewed as being sort of a big, complicated language. But it was sort of the other sort of contender in the object-oriented languages world. I think, there was a time by the early 1990s, it was like, everything's got to be object-oriented. I have to say, one of the things that is always a story of programming languages is, how are you going to structure a big program? Well, in my view, the most important thing is to have kind of a good functional design for the program, good architecture for the program, and to have sort of standardized lumps of computational work. So you're not sort of building everything. Every time you want to build some particular sub-piece, you build it up from scratch. If you have, and this has been the concept of Wolfram language for the last, basically I've been working on it for 40 years now, to identify these lumps of repeated computational work and develop them in a clean way, give them names, make sure they can operate between themselves. And that way you routinely use these sort of sophisticated lumps of computational work rather than having to drop down and rebuild things where you never build the things you're building as well as you would if you built a standardized version of it. And so, for example, one of the things has been the idea of typed languages, which is something that the idea of types in languages has been something that's existed from the very beginning. I mean, it existed in Fortran, for example, back from the late 1950s. And why did it exist? Well, because you needed to know, were you going to store that thing as an integer and with the bit pattern of an integer, or were you going to store it as a floating point number where it's a different bit pattern that represents the number, and the operations that are being done, the machine code operations that are being done, work differently because they're dealing with a number that is encoded in that different way. But so this idea of types was an idea that was a practical idea of early computers, early computer languages. It's an idea that sort of has flowed through to modern times. Things like C allowed you to start having these what you might call type products, what you would in modern terminology call type products, things like structs, where you can combine, it's an integer, it's a pointer to a real, it's an array of doubles, whatever it is, all sort of packed together in one thing. But the origination of the idea of types was kind of a nod to a piece of mathematical logic that had originated in the 1910s. That was Russell, this was a Alfred North Whitehead, Bertrand Russell production, because what had happened was this is sort of the early days of the formalization of mathematics and so on, the sort of pre-computational computation, where kind of the notion was, what was mathematics? What kind of a thing? How would you build up the structure of something that would be mathematics? And Gottlob Frege in the 1880s and so on kind of was really pushing this idea of, let's take logic as the underlying raw material and let's build math on top of logic. And so he kind of tried to set up definitions that were purely in terms of logic for things like the numbers and integers and sets and things like this, later on things like sets. And Russell famously found this kind of this bug in Frege's setup, paradox kind of thing. Russell then, then Cantor had introduced this idea of set theory. And set theory is okay when you have finite sets. You just got a collection of things and you can talk about that just fine. But by the time you've got infinite sets, it's a much more difficult thing to start talking about. But that was kind of really what Cantor wanted to be talking about. And, you then get, is the set of all sets a member of itself? Is, all of these kinds of things that eventually become paradoxical. And what Russell suggested was, in order to get rid of these paradoxes, you could introduce this idea of types. And so instead of being able to talk about just a set, it's a set with anything in it, there will be these types, and you could have these hierarchies of types. And that would allow you to distinguish these things and prevent these paradoxes about, sets that are members of themselves and things like this. So originally, types were born out of this idea of sort of avoid the paradoxes, certain paradoxes in mathematical logic. And then they were sort of, as an engineering matter in the 1950s, they were introduced into computer languages. It's only very recently, in the last, decade or so, that sort of the formal theory of types has kind of become a thing in its own right that has had importance in kind of the thinking about the sort of theoretical aspects of computation and so on. And I think this kind of gets us off topic, but I mean, this is things like homotopy type theory and so on, and these various programs for thinking about the foundations of mathematics and the sort of merged foundations of mathematics and computation that have come about, and the idea that there is a calculus of types, that you can actually sort of describe things in terms of types. In the end, what ends up happening is people, we're sort of segueing a bit off topic here, but there's a whole kind of there's a whole world of just doing things in terms of types. And for example, in the compiler for Wolfram language that we're been developing for a number of years, it's a big festival of type analysis and type computation. The big issue is, if you know this thing's going to be an integer, or if you know this thing's going to be an array of integers, you can very efficiently map that into something that is executed right down at the level of machine code instructions. But you have to know, you have to be able to prove that this thing can be, oh, it's either an integer or it's a list of 3 real numbers or something. And this analysis of types is a complicated thing. And you end up with, type products, type sums, a whole calculus algebra of types. Then you start worrying about things like the type of types, the type that represents all, the type that is, that is the type that types are, so to speak, all those kinds of things. Rather quickly, you get into a complicated hierarchy of things. The other thing is so-called dependent type theory, where you're dealing with this type is not just defined by, oh, it's an integer, it's a real, but it is defined by some property. Oh, it's an integer that has the property that's greater than 3 and less than 7, or it has the property that it satisfies this complicated Diophantine equation or something. And by the time you're doing dependent type theory, you've kind of taken the lid off things and you're doing universal computation, and there is sort of no, you end up with all the difficulties and all the undecidability issues of sort of general computation. So it tends to be the case, people say, oh, you can figure out things in terms of type theory, but that's type theory with a lid put on what its capabilities are. And that lid doesn't allow you to do arbitrary computation, but that prevents, that's what allows you to do the analysis that lets you use it to say, in this piece of compiled code, this will be that we can convert this particular, X is always can be represented at the machine level in this particular way. Okay, so in any case, types were another kind of structuring concept, and types got more elaborate. Then, I would say that the story of sort of how to organize large pieces of code. I was just going to say that I kind of think that a number of ideas have been really bizarrely missed in the history of typical programming. One is symbolic computation, and this idea that you can have an X that just stands for itself, or a thing that represents a city or something, and that kind of a thing, which if you start saying, let's talk about data types, that X, what type is that X? Well, it isn't a type. It just stands for itself. And it can be a city, it can be an image, it can be all sorts of things. You don't have to say. And in Wolfram language, for example, we've sort of abstracted things beyond the level of types. And we don't have to be talking about, is this symbolic expression of this type or that type? It's just a symbolic expression. And from the structure of the expression, you can say things about what you might consider it to mean. Like we can think of this as an image, or we can think of this as a piece of audio or something like this. And I think that, sometimes people have been chasing the wrong kinds of things in terms of sort of how to structure large programs. I think one of the things that's very interesting with Wolfram language, because it's a symbolic language where everything is about transformations on symbolic expressions. So any fragment of code, there is a meaningful thing that you can feed to that fragment of code, and what the fragment of code produces as output is just a symbolic expression. You don't need to put it in kind of a harness to say, oh, I'm going to structure this data in this way and put all these things in memory in this form, and then at the end I want it to print something. There's no need to say, oh, print something. You just hand it back a symbolic expression, and then in the usual notebook interface, there's some display mechanism for that symbolic expression. But the main point is it's just a symbolic expression that you can then go and compute with elsewhere. And so that, when it comes to things like debugging, the fact is you can sort of take your program apart and all the pieces actually operate as standalone things. That's an important idea. And I think in some of what's happened in terms of the structuring of large programs has partly to do with the fact that there start to be groups of people that work on them, and there's, it all gets enmeshed with source control systems. The idea of source control, things like Git and so on in modern times, that whole idea is very old. What is it? The patch system. I remember back when I first used online, where you didn't have card decks, where you could actually have your program in stored online, and then you would submit versions of the program. in some very bizarre way, and this was true even in the mid-1970s, you would have this patching mechanism where you'd say, here's my original code, and now I'm going to add some patches to that original code, and the patch thing is what I now want to submit. And I'm now a little bit not remembering how that all worked, but I think there was already a thing called RCS, I think, which was a patching system for code. And so this idea of sort of making differences in code and taking your original program and making patches to it, that's a very, very old idea. But that got much more structured with these kind of shared server-based kinds of mechanisms. I suppose those things were server-based as well, because they were on time-shared systems with central computers and so on. But in any case, that's yeah. So, I mean, when it comes to when we talk about design patterns and so on for languages, one of the things that as a language designer, my goal is, if there is a thing people always want to do, just give it a name and have it be a function in the language, and then that's how people can do it. Rather than saying, by the time you say, here's an idiom that you should learn that is a pattern for how to do this, that's sort of that was a step not taken by the language designer. Now, sometimes when you do language design, it's important to have a name for this lump of computational work. And if common language does not provide you a reasonable name for that, then it can be difficult. And sometimes, at a slow rate, I introduce kind of completely new names for things that are, where you just have to learn this word because it's a new concept. But you don't get to do that at a very high rate. Now, I will also say that I think there are, these different patterns for programming in general, from sort of the I would say functional programming is, in Wolfram language, I would say there's people do a tiny amount of procedural programming. That's quite rare. It's mostly functional programming or pattern-based programming. Pattern-based programming is all about, you've got a symbolic expression and you want to transform it. And that's kind of an idea for programming that's super powerful, not so popular. It was something that was in some of the early string manipulation languages, like Snowball, for example, had ideas like that. But it's really a very powerful idea. And it's something that, in a sense, is the generalization of sort of apply a function to things. Because in symbolic transformations, what you're doing is you're saying there's a pattern that is a class of expressions, and they all get transformed this way. And one particular class of expressions are things like f of x blank, that represents a function f with sort of any expression inside it gets transformed in that way. But this sort of idea of functional programming, which is kind of the, you can trace that back to things like combinators from 1920, things like lambda calculus from 1935. This idea that there is it's a bit like a mathematical function, but it is a computational analog of that, in which you're kind of having this thing that sort of eats an input and produces a result, and that you kind of think about computation as being a sequence of such functions, sort of encapsulated as the only thing that happens. It's kind of the opposite end of the world from Fortran common blocks, where there's this big global thing, and you're sort of plucking things out of this global global pile of data. It's very encapsulated. The thing just has sort of one mouth that it eats data into, and then it produces its results and so on. By the way, I mean, in very modern times, one of the things I'm interested in is generalizing those set of ideas into this sort of multi-computational world, and that relates a lot to things in higher category theory and all these other kinds of approaches. But that gets us way off track. Parmenides is commenting that they think Algol was the first to have language to have recursion. I think that's right. I mean, recursion, just to be clear, the history of recursion itself was, in a sense, you can point to things like the Fibonacci sequence, defined in terms of rabbits in previous years by old Fibonacci in 1200-ish. That's sort of an example of recursion in some sense. It's sort of thinking about a new thing in terms of older versions of the same thing. And the same, that occurred in recurrence relations. Those were extensively handled in the 1800s and things. You know, people like Boole wrote books about difference equations, which was about recurrences and so on. So as a mathematical concept, you know, f of n depends on f of n minus 1 and f of n minus 2 and whatever else. That was a pretty known thing in the 1800s and so on. Then when people were trying to sort of formalize mathematics, one of the key ideas, I should have said, one of the ways that recursion was used was in proof by induction. So, you know, proof by induction says you can prove it for the case of n, and then, if you can prove it for n, then induction means you can prove it for n plus 1. You can jump from n to n plus 1, and there's a base case for 1, for example, and therefore mathematical induction says, therefore you can prove it for all cases. And so, for example, in the Peano axioms for arithmetic, developed by Giuseppe Peano in 1880s or so, the induction axiom is the most sophisticated axiom in Peano arithmetic. The assumption that the thing I just described, if you can prove it if you can go from n to n plus 1 and you've got the base case covered, then it's true for all n. So that was sort of an example of recursion. And then when people like Hilbert around 1900 were trying to sort of formalize what is mathematics made of, one of the things that they introduced was this idea of primitive recursion, the idea of any function that you can define in mathematics can be defined in terms of previous values of that function, more or less. And that all worked very fine until Wilhelm Ackermann, who was a student of Hilbert's, discovered this thing called the Ackermann function, I think around 1920, which was a function that grows too quickly to be primitive recursive. It doesn't just look back at its values. It has this mu operator that it has the equivalent of something where that's in general recursion. That comes later with Gödel and so on. But the Ackermann function, the Ackermann function is basically the function where you are starting off with 1 plus 1 plus 1 plus 1, and times makes n, then n a bunch of times makes that's multiplication. You go from addition to multiplication, then you do repeated multiplication, that's powers. You do repeated powers, that's tetration or power towers or something. The Ackermann function is the parameterized function that says you're going in that hierarchy. It has two arguments, and one of them is what two, or is it three arguments? I think for the original Ackermann function might be three arguments that says which level of this hierarchy are you at, and then what values are you operating on. And so that function could be shown not to be primitive recursive, and so that kind of blew out the idea of primitive recursion would be the end of the story. And then Gödel introduced general recursion, etc. But this idea that recursion was an interesting construct and concept was something that had certainly bubbled up in the world of mathematical logic. Now, it's worth remembering that many of the things that have bubbled up in the world of mathematical logic were not really used in programming languages. Maybe Algol tried to use some of them, but a lot of the lessons from combinators about sort of symbolic transformations and so on really were not, I would say, seriously used. I mean, I've tried to seriously use these things. I don't think they've been very widely used. Let's see. Probably some comments on this. Hold on one second. David Brown is asking, have Julius sets and Fatou sets played a significant role in the development of computer programming languages? I think absolutely not. So far as I know, Gaston Julia, who was a mathematician in the first few decades of the 20th century, French mathematician, introduced this idea of Julius sets. That was a time when, so this field of dynamical systems theory, let's see, there was a convergence of a few different things. There had been a lot of work in celestial mechanics that had led to sort of the idealization of solving a differential equation and seeing what the solution set looked like. That had led people like Poincaré to introduce topology and so on. Meanwhile, there was a bunch of work being done on group theory and on, I'm not sure I know this history that well. The end result was that this notion of iterations, like take a number z, complex number z, and replace it by z squared plus a constant. That was a thing that people started looking at in around 1900, and I'm not sure I completely know why they were looking at that. I think it was some, well, I'm not sure, but Julia was part of that, and he produced really some quite nice pictures, as I recall, of the sets that you get from looking at those kinds of iterations. Well, but no big mathematics got built from that at that time. I think this was the theory of functional iteration, actually. This was that's right. I think this had been a branch of sort of the notion of iterating functions was something that was sort of a separate prong of just a thing that people investigated. So, but I think it was a kind of dried up. The field of dynamical systems theory took off in a slightly different way in the 1930s and so on. Then what really made Julia sets and such like, I think, famous was Benoit Mandelbrot in the 1970s, sort of developing this idea of fractals, of nested self-similar patterns and so on, of which Julia sets are an example. And I think that's what really brought them to prominence. And so far as I know, they didn't really have a, I think it's a very distant, Gaston Julia, I don't think had anything to do with anything that turned into programming languages. I think he was a pretty traditional kind of calculus analysis oriented mathematician in the first part of the 20th century, to my knowledge. I might be wrong about that, but that's what I know. Let's see. Rifftrax is commenting about structure of computer languages, and one of the things that's interesting about languages is there are very interesting abstract ideas, and when you have learnt a lot of concrete examples of things, and then somebody tells you that abstract idea, you say, aha, and you start being able to go off and use it. But for most people, when you first present them with, and here's an abstract idea, here's an anonymous function, here's some higher order, function construct, it's like, why are you doing that? That just doesn't make any sense. But by the time you've seen many examples where somebody then tells you the rule for how to generalize, it does make sense. And that's it's a thing you have to learn. It's a sort of a thing to learn about computation, just like you might learn things about, I don't know, English. You probably wouldn't be very useful to try and start teaching somebody grammar and saying, there are verbs and there are nouns and there are sentences put together in this way and so on. If you're still, learning to speak your first words and so on, you're not really ready to say, oh yeah, now I can see how sentences are put together. And I think it's the same kind of thing with sort of ideas about languages. Let's see. Very different question here from Guil. Did 18th century engineers and craftsmen make use of Newtonian mechanics? Did they make use of sort of the paradigm of Newtonian mechanics? It's an interesting question. I know that, if you're going to build a cathedral, you want it to not fall down. And, the stonemasons and the Freemasons and so on developed a lot of knowledge about how to make a cathedral that's not going to fall down. And I think, were they explicitly using force diagrams and so on? I don't think so. I think they knew certain patterns that would work. I mean, it's sort of reminiscent of what happened in something like logic. When Aristotle originally invented logic, he did it as, here are some abstract patterns that kind of describe the form of various arguments that people make. And my guess is, I don't know for sure, my guess is that in a lot of early engineering, It was kind of like, here is a somewhat abstract pattern that abstracts from the specifics of this particular bridge or this particular buttress of some cathedral or something to something a little bit more general, but it's still a pattern. It's still, this is how it works. It's not, there is a generator, there is a set of mathematical or formal principles from which you can generate all these things. It's rather, here's a pattern, follow it. I think that there was work done in the early 1800s. People were interested in trusses, kind of truss structures of, cross beams and so on. And how would you make something that was, for example, a stable truss, where, for example, if the members of the truss were rigid with respect to, let's say, compression or shearing or something like that, that you would be able to, but they were pivoted at joints. How would you make something that would be rigid? So, for example, a triangle is rigid, a tetrahedron is rigid, let's see, a cube is not rigid, right? You can, if you take, is that right? There are many structures. You basically have to have triangles and tetrahedra, I think, in structures to have something which is rigid. So if you can pivot the ends, clearly if you have a square, it's not rigid. You can pivot it and it'll squash into into a parallelogram or some other quadrilateral or whatever. And so the question was, if you have rigid members but with sort of floppy joints, what would be, what kinds of structures could you build that would be rigid? And that's a thing that I think in the early 1800s, and probably the late 1700s, was kind of a thing. That people were thinking about. And I think there, you don't really have to use Newtonian mechanics as such, because it's really more of a kind of geometry type question, what structures will be rigid. In terms of when people started to use, started to really think about forces and actually do actual computations, it's an interesting question, because people were building bridges and things like that. And I don't know, did Gustav Eiffel, when he built the Eiffel Tower, which is, the Eiffel Tower was a bridge demo, so to speak, with some pieces that are like parts of bridges, was not intended to be a permanent structure, but has turned out to be. Did Eiffel, for example, did people like that really do computations of sort of, there's this force here, and that's how this will work? Or was it more rule of thumb kind of engineering? I'm not sure about the answer to that. I think by the time, well, let me see, early things like steam engines and so on absolutely wasn't a theory there. I mean, that was, what was the motive power of heat, so to speak? I've just recently been looking at this stuff. That was Sadi Carnot in the 1820s wrote this book about the motive power of heat in French. The big question, actually, the interesting thing Sadi Carnot did was he said, oh, there've been people like James Watt and all these people who've made up steam engines, and they've tried to make their steam engines more efficient by having, this valve opens and this cold water pours in here, and then this happens and then that happens. But what's the sort of theoretical, what's the idealized engine? It's kind of like the Turing machine of steam, so to speak. What's the idealized engine like, and how efficient might it be? But that wasn't Newtonian mechanics at all. That was an argument in the end that would turn into thermodynamics. It was a quite different kind of structure. And where were the first engineering systems that were really making use of serious, we can solve a differential equation type stories? I'm not sure I know the answer to that. Let's see. I don't think the Wright brothers were doing that stuff. They were worrying about questions of control, and it was much more rule of thumb engineering, I would say. I do think that, I really don't know. I mean, certainly by the time of World War I, there were things that were being computed all the time. But I'm not sure how much there was before that. I mean, I don't know. It's a good question. I should find out. I don't know the answer to that. Let's see. Maybe a couple more here. Parker asks, why is it that Isaac Newton spent so much of his time trying to prove theological ideas? Well, I don't know so much about Newton's theology. I think he was a little bit of an outlier in sort of the tradition of the time. But, you know, theology was the prevailing intellectual framework of those times. And, you know, I would say that at any given time, there are certain sort of prevailing cultural kind of, you know, norms and patterns of thinking, and theology was a big one. I mean, theology had been the dominant place where intellectual efforts got put for a couple of thousand years, or, you know, versions of theology. And so when you look at kind of the some of the things I've done recently about the Rouliad and the idea of sort of foundations of physics and mathematics and so on, the questions that come up there about sort of why does the universe exist, and the questions about our role as an observer in the universe and so on, many of those questions are sort of almost logical questions where if you asked who's asked these questions before, the answer is the theologians asked these questions. And they asked questions about, you know, what was, if there's sort of an ultimate everything to the universe, what would that be like? And what characteristics would it have? What could you deduce from the role of us humans relative to the everything and so on? There are lots of kinds of thinking that existed, the theological thinking, that I would say are now coming back as things which, you know, after we've worked through the kind of mathematical paradigm of science, some of these foundational questions sort of reappear. But they were the pattern of thinking at the time of Newton. I mean, it was sort of what Newton was doing, you know, in his original Principia Mathematica for mechanics, you know, that was very much modeled on Euclid. It was very much modeled on sort of, let's have an axiomatization of the ideas of how mechanics works. And, you know, when it came to thinking about other things in the world, you know, theology was a dominant sort of basis for these kinds of things. Now Newton had, again, I don't know in much detail about his theological work. I do know that he had some sort of side interests and so on. Like one of the things he was curious about is he was doing, you know, things about astronomy, and he wanted to date things that were sort of ancient astronomical events, ancient eclipses, you know, and so he went back and you know, in the Bible, you know, it'll describe some, I don't actually know if there are eclipses described, but wouldn't be surprised if there were, at least by implication. But then, so what Newton wanted to do is he wanted to figure out, you know, that eclipse that Thales, you know, famously was supposed to have predicted in some, that caused what the Greeks and Persians or something to just sort of forget about the battle because something too funky was happening when there was a total solar eclipse. I don't know what the true story there is, but there's various sort of, you know, versions of that. But so Newton wanted to know, well, when was that eclipse? And so his very last book, I have a copy of it actually. It's not one of his most famous books. It's called The Chronology of Ancient Kingdoms. And it's an attempt to go back and understand when did those things actually happen. It's not particularly successful. I mean, it doesn't get things that well correct, but it's sort of an interesting version of that. You know, I think Newton, you know, at the time when Newton was working, you know, he was a professor in Cambridge. There weren't very many professors. He was the Lucasian professor of mathematics in Cambridge, I think. Mr. Lucas, who endowed that, was just, you know, Newton was not the like incumbent number 3 or something of that professorship, and it was a rare thing to have a gig where you just got to do sort of professoring all your time, and he got that. But Cambridge was a school that was primarily training people to become, you know, to go into the church, and so it was certainly a thing that you had to be sort of, you know, involved with and aware of the whole kind of theological story. And I think probably, you know, people would have been shocked by Newton's, you know, I don't know, Trinitarian, I forget what the exact details of his religious setup were. But I think that you kind of had, that was the ambient environment in which you operated in the university at the time. I mean, people might say, rather perhaps uncharitably, I don't know, that in some universities today there's a certain kind of sort of cultural belief system environment where everybody has to believe in this and that and the other thing, and if you're not I don't know, if you don't believe enough in social cause XYZ or whatever, then then you can't really, then you'll get ejected from the university as being too shocking. And in Newton's time, if you didn't believe in this or that aspect of some theological thing, the same thing was likely to happen. So I think that Newton was probably studying that. It's partly for those kinds of reasons. Let's see. Okay, Lawrence asks, and I should stop soon here, but when will Moore's law expire? It's talking about, I haven't seen this particular announcement about a 4-nanometer technology. So Gordon Moore, founder of Intel, had sort of made this statement, computers are going to get, what was it, twice as fast every 18 months or something. And for quite a while that was happening. And then it stopped. Last decade or more, that hasn't been what's happened. I mean, I know this with painful reality, because when we first built Wolfram Alpha, for example, I was assuming that curve would continue. And so certain kinds of things, it's like, look, don't worry about how fast this is right now, because in a couple of years it's going to be faster. And turns out that didn't happen that way, because there was kind of a limit reached where, in terms of an individual core in a computer, that's how fast it runs. Now, there's been a progressive speeding up of the clock speeds. 2 gigahertz or something is a typical kind of clock speed today, and has been for a while. That hasn't been dramatically increasing in speed. I think what's been being done is the gradual tweaking of sort of semiconductor technology and the reducing capacitance and so on, so that you can increase the clock speed, reducing feature size, so you can put more features onto a silicon, onto a chip that doesn't have imperfections in it and so on, doesn't have crystal defects and all that kind of thing, and then ways to work around those crystal defects and so on. There's been sort of this gradual thing going down. 5-nanometer processes are sort of a common thing today, and you have to sort of build a whole new factory often to support sort of getting things as clean and perfect as you need to achieve a sort of a greater level of smallness in photolithography and so on. And I mean, essentially now the question is, are there other technologies, quite different technologies, that you can use that don't just involve, etching channels out of silicon? And the answer is undoubtedly yes. And in fact, sort of some part of the quantum computing world has nothing to do with quantum, but it does have to do with using other physical methods to support computation. And an old idea was to use Josephson junctions, superconducting Josephson junctions, to do computation. There are ideas about using photons to do computation, optical computing. Both of those sort of have their brand as often quantum computing today, but ultimately they're just a different kind of approach to using sort of physical things to do computation. And certainly my own principle of computational equivalence and so on suggests that you can make computers out of almost anything. The question is really what's convenient to engineer computers out of. And I happen to think there are lots of things that you could engineer computers out of that are different from the things that have traditionally been used. But I think the thing that's really happened with computing is, insofar as their speed increases, it's because things went more parallel. What was, you go through an array and you do an operation on each element in turn, becomes a GPU that's an array processor where you have separate hardware to operate on each element of the array, and you can just do the whole thing in parallel. Or where you're doing things where you say, speculative execution of instructions, where you have your CPU and it's saying, well, let me go ahead and I don't know which way this if statement's going to branch, this conditional is going to branch, but I'm just going to try and pre-compute what happens on both of those branches. And I'm going to prefetch the things from memory that I might need. Those kinds of tricks are being used to try and speed things up, even within the context of existing software. One of the big dividing lines is, can you take an existing large software system that's ultimately written in like C or nowadays in something like LLVM, that's kind of low-level generic machine language type system that lots of compilers target. Can you take something written in those kinds of languages, and can you run it sort of raw on your computer, or do you have to re-architect your program in order to have it to be able to run on your computer? And I think one of the things that's been sort of a challenge for GPUs is that, in a sense, one of the things that wasn't obvious they were going to work out that way is you have to, it's particular pieces of code that are specially programmed to run on GPUs. It isn't, oh, let's just take our generic program and somehow magically have it run faster on a GPU. No, that's not what happens. It's not what's happening when you make things that run in parallel. You have to think about the fact, oh, I want to run this in parallel. When I use in Wolfram language, we for a long time had parallel computation primitives, and I do a parallel map or something. I'm running in parallel across a couple of hundred computers, let's say, but I have to think to do that. And there are some internal operations that automatically do it, but it's not something where it's sort of, you just take existing software and just say, oh, now I'm going to put it on the magic parallel machine, it's going to go faster. So there's sort of a question of whether there's a whole other level of software that could be built that is sort of born sort of more parallel, born more able to take advantage of what physics can offer, and the fact that in physics, there can be things that are in different places in space that are running at the same time. It could be the case that physics was just purely sequential, but it's not. Physics has built-in sort of parallelism across space and so on. And so the question is, can you fundamentally take advantage of that? In a sense, our whole multi-computation initiative is a bit about that, although it goes even a further level, which is when there are multiple paths of history, you could be following all those different paths, even though they're inconsistent with each other. Even though there are different branches you could take, and those kind of lead you to different places in branchial space. Just like you can lay out computations in physical space with different sort of elements of arrays and things, so you can lay out computations in branchial space, where you're sort of taking the different branches in the conditionals and so on, and those represent this sort of set of possibilities. And so kind of it's sort of an interesting thing to kind of think about how computation can get sort of decomposed in these different ways. And I think one of the things I've been realizing recently is this kind of time-like computation, where you do a computation, you take the result of that computation, you do another computation. It's a sequence of things through time. So there's sort of a causal dependence chain that goes from one computation to the next and the next. Then there's sort of space-like separation, where you have things which can happen at sort of separately in different places in space, all sort of parallel in time. And then there's branch-like separation, where you can have things which are sort of happening as different branches of possibilities, and which can, for example, merge in the future because both branches lead to the same result in the end, or maybe they don't merge in the future. But this kind of space-like, time-like, space-like, branch-like, time-like separation, I think, is a useful way to think about computation. And we're just sort of, people have been doing some sort of space-like computation with array processing forever and ever. And, in Wolfram language, for example, we have the kind of notion of listable functions and so on, which just sort of take as one gulp this sort of parallel thing to be done across lots of different elements. I would say branch-like separation is much less well understood in programming. I mean, that's really the story, sort of when you have these different branches and they don't converge to the same thing. When they do converge to the same thing, that's sort of an eventual consistency story. When they don't, it's kind of what would be called a race condition. It matters which one actually happens first, because that's what determines what really happened. There are two branches of possibilities, but there's still a really happened notion. And so then the question is, how do you, in a kind of organized way, think about the sort of the different branches of what might happen? And that's what one of my current projects is looking at, sort of our multi-computational paradigm that's arisen from the physics project, and where we talk about different observers of this sort of set of branching possibilities, and it's kind of partly a story of quantum mechanics, partly a story of relativity. Those ideas get immediately imported into distributed computing, and that's a coming soon attraction, I hope. All right. I think Gordon is commenting that that computers nowadays are more powerful enough for the average user. What's so strange about that is that, like the computer that I have sitting in front of me right here is, it's a little laptop, and it's kind of a generic laptop. And, sometimes running these live streams, the thing's fan jumps, starts up, and it's like really straining. And it's like, really? I mean, that's, what's happening is that there are always these things like video, for example. Video is still straining to computers in some ways. Now, the interesting question is, some other things, like, for example, when it comes to text, it's hard to strain your computer with text because, humans only read text at a certain rate. And, we have a certain built-in timescale for that. When it comes to audio, it's become pretty challenging to strain your computer with audio because, humans only ingest audio at a certain rate. We can go up to, I don't know, 20 something kilohertz or something of our ears, depending on how agile your ears are. Maybe you can reach 25 kilohertz or something, but it's still low data rates. For for a display, our eyes are more in the gigahertz type range in terms of is that right? We've got 10 million nerve fibers, and we've got, yes, that's right. And we've got some number of tens of times per second of data that is transmitted through our visual system. And so that's still a bit of a strain for computers of today. It probably won't be for that much longer. And it will be the case that sort of things of direct human relevance will start dropping below what, becoming what easy for computers. And the question is, well, what other things are there that, what then becomes the difficult stuff for computers? Now, as somebody who's interested in science, for example, there are always difficult things that I have for computers to do. But, there are things that one can imagine, like, for example, creating, in game-like environments or in virtual worlds, creating the whole sort of simulating. Well, actually, yes. I mean, one thing that's always going to be hard is simulating physics and simulating what happens in the world, because after all, the actual computation that's going on in the world, and we now think we have sort of a fundamental theory of physics, and we know that physics is ultimately computational all the way down, but the amount of computation that's being done in every, cubic centimeter of universe is very huge. It's huge compared to what our computers could possibly do. Necessarily so, because our computers are ultimately made of that same stuff that makes the universe. So it's not surprising that the computers under our direct control have less that they can do than the sort of intrinsic computation of the universe. But, when it comes to simulating things that happen in the universe, that's a thing that's always going to strain our computers. Now, then the question is, well, what about the things we care about that are happening in the universe? And that becomes a more nuanced question of how far you have to go with the computers. Now, people say, well, what about like things like quantum mechanics? Well, in our models, we kind of understand how quantum mechanics works. And it's this kind of multi-threaded sort of process where in the end, the thing we as observers notice is just some combination or slice across all those different threads. But the way the quantum mechanics is working inside, it's all those different threads. And that's, again, for the universe, it's just what it does. But for our computers, that can be a challenging thing. Whether it matters is unclear, whether it actually, by the time you as an observer are cutting across all those threads and measuring something that you can sequentially experience, because our experiences are sequential, whereas quantum mechanics is running all these different threads in parallel. When we come to experience things in the world, our experience is fundamentally an experience of a sequence of things having happened. So we're sort of we're pulling down that sort of quantum parallelism. And whether it ultimately matters that there was that parallelism inside, that's an interesting question of sort of the shadow of quantumness and how well that's cast on things once we actually observe them. Well, anyway, so I think this question of what will be the places where where sort of we'll always have more computation to do. Certainly, there are questions in science where the fact science is sort of an endless frontier that's kind of guaranteed by computational irreducibility and undecidability, that there will be questions in science where the only way to know the answer is just to keep computing, and there will always be surprises. And that sort of drives one direction of you always need more computation. Another one is the physical universe is, you'll never be able to get down to the level of all the computation it does, but there are parts of it that we might care about that still need a lot more computation. So I think there will be places where there's still sort of more computation to be done, although there are certainly places where it drops below. Computers are fast enough that for any human purposes, you click it, and yes, it did take 100 milliseconds to respond, but you'll never notice because we're just humans with our sort of human rate of brain processing and so on, and it doesn't make much difference if you that 100 milliseconds, let's cut it down to 50 milliseconds. Okay, great, nobody's going to notice. But still, there are things where there's enough bulk of computation that it does make a big difference. All right, well, we should probably wrap up there. Thanks for lots of interesting topics, and I see many more that I didn't have a chance to cover today. I'm going to make a small pitch because I'm about to dive into another kind of historical investigation that I will write some stuff about. This one is about the history of thermodynamics, a very interesting and confused history, which I actually thought I understood, but have discovered new things about. But, I do write a fair amount about, and have written a fair amount about the history of science and technology, and you can find that on my writings website. There's a category for historical perspectives, and I think some of those things are pretty fun to read, and I encourage people to take a look at them. Some of them I've even done as kind of spoken podcast type things, and I'd actually be interested if people think that those are a good idea. Give us some feedback about that, because it's pretty easy for me to read those things, and usually I embellish them a bit as I'm reading them, because I think of other stuff as I'm reading through what I wrote before, and be interested to know whether people would like to see more of those or hear more of those. All right, I should wrap up for now. Thanks very much, and bye for now.